because these two are the same. It is because when you make the book square, it's still one.
Not with that attitude. Oh, I know. Actually, you do understand that. Oh my goodness! Now you can get it down the head with that statement.
Because he's still there on both sides. Technically, we could just tell him.
You can just do one side of the mirror.
Instead of doing all points, he's going to do.
Oh, all of it on one.
Oops.
So, real quick, you can imagine, I made x2, negative 2, 3, negative 3, 4, negative 4. Like at 4, at 2 it's nice, right? If x is 2, it's 1 minus that. So it just lifts the original one up by 1. If it was 4, it would be 16 over 4, it would be 4 minus, so it lifted up by 4. Do you see how it's just a bunch of parabolas kind of going up? So what I've done, what this ends up being, these traces of the surface, if I graph that z equals equation, that of course is a how many dimensional shape? Three-dimensional shape. So if I look at from the YZ plane, I'm taking it and just condensing it. I'm doing that to it, so that when I say this is 0, this means when x is 0, this is what the cross section looks like. When x is 1, this is what the cross section. This is plus or minus 1, of course. Does that make sense? You guys say that with me? So if the x-axis, of course, is coming through here, then one of these will be here, and the other one will be one back from there. Does that make sense? So they do overlap when I compress them, but when I pull them apart, then they go right there. So what we're doing is, we got this 3D figure. I'm going to show you the result, and I'll show you how you can see all of these on the result. It's really nice. And we're just doing these cross sections, right? That's why I was thinking, what is that? Is it an MRI that does that, or a CAT scan? I always forget. That the cross sections of your brain without actually having to open you up and slice you up. All right, well, okay. None of us are medical people, I guess. All right. You've all seen one photo where they slice through you without actually slicing through you, which is nice for your continued life, you know. So what about this guy? It's just going to be a bunch of up parabolas. So now x is 0, z is 0. When x is 2, z is 1. When x is negative 2, z is negative 1. Something like that. What am I trying to say? When x is negative 2, z is 1. There you go, Jeff. Blah, 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 blah. And for this, it's just going to take that parabola and do what to it? Shift it down by 1/9. So basically it's going to be the same thing just about, just right below it. Right? You guys semi with me here a little bit? A little tiny bit? And if I made y equal to plus or minus 3, that would shift it down by 1, for example. Right? So as I move away, what plane am I operating in? What plane is this? This is the XZ plane. So if I'm on the XZ plane, it's going to go through the origin. If I take a step back this way from the XZ plane, it's going to move down. If I move this side of the XZ plane, it's going to move down also. So it's these parabolas that are coming up to it and then going down from it. I don't know if you guys can, and again, it's going to be easier when I pull up the little program. So we're just looking at it from looking at it straight on at the YZ plane for the first part. And that's what it looks like as it's coming at me and going away from me. And then I move over here and I go out from the XZ plane. What does it look like? Oh, it's up parabolas. That's freaky. What the shit is that going to look like when you slam them together? But I got a third one. I can look from overhead. I can look at the XY plane and see what it's doing. And this is where things get a little freaky. What happens when that Z is 0? And x squared over 4 equals y squared over 9. I get x equals plus or minus 2/3 y, or even better, y equals plus or minus 2/3 x, 3/2. There you go, check. You guys see what I just took the square root of both sides, plus or minus? It'd be better to put that over there to make it look more like a mx plus b kind of thing. So when z is 0, it looks like straight lines. All right, well that's really exceptionally freaky. With a slope of 3 over 2. So 3 over 2. Down, 3 over 2. And then it's plus or minus, so it's also going to be over this way. It's also going to be over this way. So it's these lines here. That is exceptionally freaky. And again, we don't know how to take this. Now where things get more interesting is, what if z is 1 or negative 1? I get 1 equals x squared over 4 minus y squared over 9, right? What's that the equation of?
Hyperbola.
Hyperbola. Sitting on which axis?
The y-axis.
So, I mean, the quick way to think about it is, it's sitting on the positive variable's axis, because are there any real y-intercepts? Are there any real y-intercepts? Are there any real y-intercepts? How do you find the y-intercept? Why am I doing this? How do you find the y-intercept? Make x 0. Try to solve that. Give me a real number. Can you do it?
No, there's
No. Alright, so then it's got to be sitting on the axis that it can actually hit. Does that make sense? There are no y-intercepts, so how could it be sitting on the y-axis? So hyperbolas always sit on the axis of the variable that's positive, right? Why? Because of what I just said. Okay, so I know some of you guys are like, hyperbolas? What the hell? Yeah, freaking hyperbolas. Of course, what's the 4 and the 9 tell me?
x equals 2.
Yeah, I go out 2 on the x, and I go out 3 on the y, 2 on the x, 3 on the y. Put a little open circle on the y because it can't hit the y-axis, right? You remember doing this stuff? Make a little box. You draw the little... But these are going to be my asymptotes. Do you see that? Those are my asymptotes. So I can just draw... You can make the sound effect if you want to. Or not. So this is if z is 1. Right? What if z is negative 1? What happens?
It's going to be on the y, sitting on the y.
Yeah, because now I got freaking negative 1. I got to multiply by negative, so I get it in the right format. And oh shit, now it's sitting. Become a minus. Now it's sitting on the y-axis. So now it's just going to be like this. Is that cool? So this will be negative 1. Negative 1. So I really, now let me, I don't know. Do you see, I'm trying to tell you, I'm not, I know you can't tell sometimes with me, but I try never to be like, I'm not talking down to your side. This is not an easy thing to do at all. Combine all 3 of these into a single 3D image. Not easy, not impossible. Alright, so you just pick somewhere for your origin of A. So here's my x, y, z. So let's look at xz first. Here it is. Here's xz, right? In the xz plane, it looks like, I didn't really do these, but remember this is the xz plane and then it shifts as I move away from it. So in the xz plane, it looks like this. There's 0, Then it went over 2 and up 1. Over 2 and up 1. So there's my parabola in the xz plane. And if I move away from it, let's do the smart thing. Now watch. If I move away from it by, what did I want to do? 3 on the y plane. Why would I do that? So move away, right? If I make y equal to 3 instead of 1, then this is going to be 3 squared. It's going to be 1. I think I see what I'm doing. Right, instead of doing freaking 1/9, let me go ahead and take it back to 3. Now it's going to be down by 1. So it's going to be down by 1. And then it would move over 1, 2, up 1 has to be down by 1. Just moving everything down by 1. So I'm going to repeat that same picture. But when I move 3 away, it's going to move down by 1. Because it's minus y squared over 9. So now it's going to move down 1. So it's like this. But as I move away from the plane, it does like this. Does that make sense? If I move towards you, it does like this. It goes down in both directions because it's minus y squared over 9. So it's like this. I feel like I should have some Russian music or something. I can't do that shit. Alright, and then over here, it would be over 2, up 1, down 1 again.
Can't see it.
Oh, sorry. So all I did was I took this and I moved it down 1. I took this and moved it down 1. I took this and down 1. And it would do the same thing on the other side. And then going this way is going to be, if I look at the YZ plane, it's going to be a bunch of down parabolas. Okay, so let me just jump to the chase here. I want to show you 2 things. I want to show you a kick-ass website that will help you out immensely to see these 3D objects. One thing it's got an advantage of Wolfram is it's completely free, but it only does graphs. It actually was created by a student of mine in last semester's 281 class. This kid knows computer science like crazy, so when he learned some of this shit, he's like, look what I just did. I'm like, holy crap, dude. So, this is what you get with this equation. Let's see what we get with what we got here. What's it? X squared divided by 4 minus y squared divided by 9. And now watch. That's freaky looking. What plane am I looking at right now? Can you guys tell? Well, let me see if I can turn this thing around. So we can get this to a place where we're used to. Ooh, does everybody feel sick a little bit? Yeah, here we go. So this is the XZ plane here, right? And what we say in the XZ plane, what should it look like? What kind of parabola? Up parabola. Look, this cross sections, do they look like up parabolas as I'm looking in that direction? They go up to the maximum at z equal to 0, and then on the other side, they go down again. Do you see that? But they're up parabolas here. Do you see that? Up parabola. I love the little thing he added. I asked him to add this piece, and he did. Oh, shit, you guys. Can you see that cross-section? No. Can somebody turn out some lights for me? You guys are kind of funny, because you can't really see that too well. There. Now, can you see that cross-section I'm talking about? See? The up parabola cross-section? Do you see that? Do you see it? Yes. You're not saying anything, so I'm not sure. Wow, that opacity really went away. All right, well, now you can definitely see that thing, right? Now, if I look at it from the here I am, XZ plane, right? The XZ plane should be down parabolas, right? Where am I at? YZ. YZ. And you see how it has a minimum, and then as it moves away, it moves up. That's what we discovered, isn't it? As you moved away, it moved up. You can see that happening here. It's kick-ass. And of course, if I look at it from above, this is where the weirdness happens. Look at that. There's the lines, and then if I move away from it, oh shit, sorry. There's those. There's those. Woohoo! Woohoo! Woohoo!
Now, are you technically looking at all 3 planes at this point? Or is this
Those lines he added show up cross sections for all 3 planes at once. So you have to be a little careful what you really want to look at. I'm looking from above, so I just want to focus on those. But it's still. So you ready for this? Can you guys see what the URL is for that? Plot.ninja. Easy to remember. If I am you, I'm using the shit out of this thing.
Not great.
Wolfram Alpha is decent, but it can get a little clunky, to be honest, because it actually isn't only a math thing. It does too many things. This is purely graphing math stuff. If I'm you, I would play with this thing like crazy. I didn't assign too many 3D drawings for you to do, but there are a few. And so if you haven't gotten your 3D graph paper printed out, you desperately want to do that. Right? And it just depends on how good of a drawer you are. So I'm going to be a little lenient, because I am not a very good drawer. Right? Can't even say the word. Okay, what time we got? Oh, we got a little bit of time. Can you bring the lights back up? Oh, everybody's like, this means we get to go. No, it don't. All right. Aww. So disappointed. Yeah, a little preview of chapter 13. Oh, before we leave section 12.6. Before we leave section 12. The main thing you as a student have to worry about with 12.6 is the traces. That's the real place you're going to be working with. One big part of section 12.6 is this here on page... something. Hold on. So they give you the form, and they tell you what the result would be. So it kind of makes sense this guy's going to be an ellipsoid, because ellipses are based off of adding the squares, right? So no matter which two variables you leave non-zero, you're going to get these ellipses, right? So you can kind of see that happening in the cross sections they're trying to show you. Maybe. This guy, elliptic paraboloid, why does it not go down below? Yeah, z is not squared. If z had been squared, what would it look like?
It would have came to a con and con.
Yeah, it would have done like this and then had a mirror image below it, wouldn't it? And real quick, while we're talking about it, do you see how this is a hyperboloid of one sheet? Is this here? See the z squared over c squared? There's a little one there. Stay with me now, this is kind of neat. I wish they would have pointed this out. Okay. What I always hated was they give you these two things. And you can see how maybe this is an extreme of this. So how do I kind of move along here? Well, if I change 1 to -1, right? But you see how it connects with this one is, if that would have been z squared over c squared, this would be if I made this 0. That's the connection between them, right? So if this side is positive, you get this. If I make this side negative, I get that. If I make this side 0, that's the what do you want to call it? The midpoint of the two. Does that jive? So that morphs into that, morphs into that. If that would have been z squared over c squared with a mirror image on the bottom. So I'm not going to make you memorize these forms. Are you with me? When you do the homework, though, some of you guys would normally freak out. Just go to this page. They're going to ask you, match the equation with the image. All right, well, match the equation they give you with these equations and figure out what the hell it should look like. So you're just getting used to the equation and what form it would take. And hopefully it makes sense. If there's any minuses anywhere, there's got to be hyperbolas in the damn thing somewhere. Right?
You're going to ask you something like that on the test. Match them.
Yeah, but I would give you something to work with, just like this. Yeah, I'm not going to make you memorize these formulas. It's just a little too many of them. But if I gave you a formula and asked you create the traces, I'll let you do that. What shape would this take on? I give you those shapes. Why would it take that shape on? That kind of thing. I would ask you all day long. Cool. This is the most interesting one here. What does that guy down here look like? Let me say one word. Horses.
Saddle.
Saddle. This is where you get the idea of a saddle point. So that's going to become important when we start doing calculus to these things. You know, this is freaking calculus class. We are right now laying the groundwork for functions, vector functions and stuff like that, surfaces in 3D, and then of course we're going to have to talk about taking derivatives, doing integrals. What would derivatives mean here? You got multiple directions to go in now, so now I got to talk about directional derivatives. Depending on if you're facing this way, is it going up? If you face that way, is it going down? This is in our future. All right. And then chapter 13, a little preview. I love you guys. I spoil you guys.
I thought Cut 2 was more easy.
13, I'm okay with us getting into it later than I thought, because 13, you please notice there are limits, right? Old news, old news. If you have trouble with those, maybe go back and firm up now, because that should be quick. Little limits. They give you a function. So now we're going to do stuff like, I'm going to give you a function r of t equals cosine t sine t t. Just a minute. So technically I would call this one-dimensional, right? Do you guys see why? Because it's controlled by one parameter. Now what would that look by itself? What would that look like? Cosine t sine t. Parametric equations, x equals cosine t, y equals sine t. That would trace out a circle. Yeah. Right? X equals cosine t, y equals sine t. You get a circle when you trace that out. Now, what is this doing? As t increases, this is the what component? Z. So imagine I'm walking on the xy plane. If that wasn't there, it would just be a circle. That is there. So now, as I move, what's happening? I'm tracing out a circle, but it is coming up. Because the z component is increasing as the inputs are increasing. So it keeps drawing a circle up, but it's like a spring somebody stretched. Now it's only that. If this was 2t, it's stretched even more. 1/2t, it's not stretched. 0, it's in the xy plane. So we're going to be doing limits of these that leads to derivatives of these. Right? It's going to be derivative by component. That's nice, isn't it? As long as you know how to take derivatives, you know how to do derivatives of vector functions. Okay, I had to get that out there.